Log on, tune in, find out. Another good idea from Cambridge.
Manor Mendel, and the title is Prof Theorems for Metric Spaces, please.
I will begin with definition of ultrametrics. I apologize. I will start slowly, because people from varied backgrounds here. But I promise that by the end of the talk, I will zip through the slides. So, one of you that need prefer it this way, will get it. Okay, so ultrametric is a special kind of metric space in which the triangle inequality is replaced by the ultra-triangle inequality. The distance between x and z is most the maximum between x and y y and z. Okay, and we're going to talk a lot about ultrametric, so I want to explain it a little bit deeper, slightly deeper. So here's a property of the ultrametrics. It looks like that. What you see is clusters in which so if the diameter of this space is delta, you see clusters in which the inter distance between the clusters is the same as the diameter, is also delta. And if you look on each of the cluster, you see recursively the same picture. And this follows immediately from the inequality above by considering the relation x and y are related if their distance is less than the diameter. And the ultra-triangle inequality implies that this is a transitive relation, which means it is a equivalence relation. So you can take the clusters to be the equivalence classes of this relation. And you can continue this way on each of the clusters. And here is another alternative view of ultrametrics via rooted trees. In this tree, the points of the space are the leaves of the tree, if the space is finite, or the branches of the tree, if the space is infinite. And the distance between two branches is okay. It's a rooted tree with labels on the vertices. The labels are non-increasing when you go down in a branch, and the distance between two branches is the least common ancestor. The label on the least common ancestor. And you see that this corresponds to this picture, where the root corresponds to the whole space. Its children corresponds to the clusters that you see here. The labels correspond to the diameter of the respective clusters. So it's the same picture. So this is ultrametrics. Another standard definition is the distortion, the same thing that Tassos talked about in the previous talk. The distortion of embedding is the smallest capital D, such that the distances in the image are at least the original distances, and at most capital D times the original distances. And we allow a scaling factor, A. So we'll embed, in this talk, we'll embed in ultrametrics. Ultrametrics are closed under scaling, so it doesn't really matter. Here's an example for the distortion. Take this star graph and look on the graph metric on it. Try to embed it into Euclidean, three-dimensional Euclidean space. Here's a specific example of embedding. You can embed the center into the origin and the leaves into the axis, and you see that the distortion here is square root of t, because the distance between two leaves is contracted by a factor of square root of t. It becomes square root of t instead of 2, square root of 2 instead of 2. And if you didn't see it, it's a nice simple exercise to find the best embedding. This is not the best embedding in the Euclidean space, so if you don't interested in my talk. If you're not interested in my talk, you can think about this exercise. But let's switch gears. So ultrametrics are very nice. Kind of metric spaces are Euclidean, they are trimetric, they have this hierarchical clustering property that I just talked about in the beginning. So we would like to find ultrametrics in metric spaces. Let's look on specific metric space, a path of length n. And let's try to embed it into ultrametric. So assume the embedding is non-contractive, then the ultrametric that you can define on this path has diameter at least n minus 1. Now we call this structure of ultrametrics that I just said in the beginning, that you should have, in ultrametric you should see clusters, somewhere clustered on this path. And this means that you have an edge that crosses the cluster. Now the distances in the ultrametric between the cluster have to be at least n minus 1. So you have an edge, you start with non-contracting embedding, you have an edge that is stretched by a factor of n minus 1, at least n minus 1. So this means that any embedding of the path metric into ultrametric has distortion at least n minus 1. And this fact is sometimes useful, but usually we don't like that high distortions. But still, there are non-trivial embeddings of arbitrary metric spaces in ultrametrics. I'm going to talk about a specific one in this talk. I'm going to look on a Ramsey problem related to ultrametrics. And the Ramsey problem is the following. We want to find in arbitrary metric space a large subset which is an ultrametric. Okay, this is natural Ramsey-like question for ultrametrics. It has variety of algorithmic application which I'm not going to talk about in this talk. But even this is not really possible because of this trivial example. Any 3 points on the line satisfies the triangle inequality with equality, which means that it don't satisfy ultrametric inequality, the ultra triangle inequality. Which means that if you try to extract ultrametric subset from the line, you have to be satisfied with 2 points. This won't be good enough for us, so the solution that we're going to work out here with is to use small distortion, to allow small distortion. So I can now formally state the problem that we consider in this talk. We'll consider 2 variants of the problem depending on the interpretation of size. We want to extract large subsets, so we'll use large, the sense of large, and we'll use. So the first variant is essentially due to Bougain-Figel and Millman. In the following problem, you are given distortion capital D and the natural number n, and we are looking for the largest case such that in any n-point metric space we can extract a subset of size k, which is approximately ultrametric up to distortion d. This is the first variant. The second variant is essentially the same, but we replace the cardinality with the Hausdorff distance. It's more suitable for infinite spaces. So now n and k will be real numbers, and we want to extract from any n-dimensional space a subset S, which has dimension at least k, Hausdorff dimension at least k, and is embeddable in ultrametric with distortion D. This question was asked by Tao, asked in private communication. Before talking about this problem, let's see what it means to be de-embeddable in ultrametric. What it means to be distorted ultrametric by distortion D. So if you recall, in ultrametric of diameter delta, we had cluster in which the interdistance was also delta. So in distorted ultrametric, the interdistance in between the clusters is at least delta over d, and you have the same thing, the same invariant in recursively in each of the clusters. This is distorted ultrametric. And what we want to do is, given a cloud of points, we want to find, of diameter delta, we want to find clusters of points in which, with interdistance at least delta over d, to sort out all the points outside of this cluster and continue recursively this way and find a Ramsey subset, which is obviously d approximate ultrametric. And of course, the real challenge is to find, to do this process while retaining enough points, so subset will be large. Let's look at an example, endpoints on the line, and we want to find the ultrametric inside it. So let's take a concrete example. We want to find a 4 approximate ultrametric, large approximate ultrametric. What we'll do is throw out the middle 1/4 interval and continue recursively in each of the remaining intervals until we reach intervals of length 5, of diameter 4, in which case there are already 4 approximate ultrametrics. So here we have another point to throw away. And you can define the ultrametric in this way. It's obviously 4 approximate ultrametric. Okay? This is the largest possible construction of ultrametric in this case, and you see that the number of points left is roughly 2 to the power of log n base 8 over 3. Okay, this is just because at each step the size of the interval decreased by a factor of 3 over 8, and the number of intervals multiplied by a factor of 2. And if you generalize it by throwing, instead of 1/4 of a fraction of the interval, you solve the middle epsilon fraction, what you get is a set that's embedded with distortion 1 over epsilon in ultrametric, and the number of points left is roughly this thing, which is roughly n to the power of 1 minus constant time epsilon. Okay? And this is basically the best possible for the line. And the reason I'm showing this example is that we'll be able to extract, to have this trade-off, 1 over epsilon and n to the power of 1 minus epsilon in general metric spaces. So here is a bit of history of this problem. So the inspiration for this question comes from a theorem of Dvoretsky from the 60s, which basically does the same thing but for norm spaces. He showed that any n-dimensional norm space have a large subspace, linear subspace, on which the induced norm is 1 plus epsilon close to a Euclidean norm. And we also have nowadays, this is due to Millman, and we know that we can take the dimension to be even log n. I think the first tool to consider this problem in the non-linear setting where, as I said, Bougainville and Millman, they proved the following theorem. They showed that in any endpoint metric space, there is a subset of size log n, which embeds in Hilbert space with distortion 1 plus epsilon. And they further show that this is tight, at least for distortion 1.01. They show that there exists example of metric spaces for which endpoint metric spaces for which every subset larger than log n has Euclidean distortion at least 1.01. So this is actually embedding into Hilbert space. I talked about the embedding into ultrametrics. But if you look at their proof, they actually embed it into ultrametrics and use the fact that ultrametrics embeds, at least separable ultrametrics embeds in Hilbert space, isometrically. Okay. This question was also studied by computer science scientists, which were, because it has application for lower bounds on some optimization problem. There is a sequence of paper by Karloff, Robani, and Rabid, Blam, Karloff, Robani, and Sachs, Bartal, Bolobash, and myself, and Bartal, Linear, Noor, and myself, in which you see that the for distortion 4, or at least you see that they're able to extract larger and larger ultrametric subsets. And if you look carefully, you see that already in the second line, Blam, Karloff, Robani, and Sachs were able to extract a subset which is significantly larger than log n. This is in contrast to the lower bound that I told you Bougain-Figueira and Millman proved. So there is no contradiction here. They proved it for distortion 4. Bougain-Figueira and Millman has this upper bound of log n for distortion 1.01. And indeed, it turns out that there is a phase transition here. And the phase transition occurs at distortion 2. Below distortion 2, the right quantity is log n, so you can extract only, there are examples in which you cannot extract more than log n point, which can be embedded in Hilbert space with distortion d, when d is smaller than 2. And above distortion 2, we can extract a polynomial number of points. I mean, for any d larger than 2, there is some alpha d larger than 0, and you can extract from any n-point metric space a subset of size n to the power alpha d, which can embed with distortion d into ultrametric. Okay. It's now natural to ask how alpha d behave, how this power behaves when d tends to infinity. And well, you can guess it tends to 1. And this is the right guess. It actually behaves this way, 1 minus constant over d. So this is, so okay, this was proved a little bit later by Noor and myself. And another way to say it, as I promised you in the beginning, is that we can extract, for any epsilon, we can extract a subset of size n to the power of 1 minus epsilon, which can embed with distortion 1 over epsilon, or constant over epsilon in ultrametric. And here is the outline of the proof, or at least the outline of the first half of the proof. So we have this ultrametric, this general metric space here of some diameter. We take a partition of this ultrametric, of this metric space into cluster of diameter delta 1. And now in this partition, we take only the points that are padded away from the boundary of the partition, epsilon bounded away from the partition. Now we take another scale, delta 2, and we do the same. Take points that are epsilon delta 2 bounded away from the boundary. And we do that for all scales that, let's say, in some geometric, all scales that are power of 8. And we take all the padded subsets that we found at all scale and take their intersection. So this is, the example here uses only 2 scales, but you you can imagine that they can do it on all scales and take the intersection. And this is the subset that, the Ramsey subset that we find. And it's obviously 1 over epsilon approximate ultrametric. Okay, because at all scales, the distances are 1 over epsilon, the diameter, relevant diameter. And the problem is how to guarantee that the surviving subset is large enough. So fortunately, there is this lemma that says that for any finite metric space, there exists a probability distribution over partition of the metric space with the following property. All the cluster and all distributions have diameter at most delta, and for every point in the space and for every parameter t, the probability is that this point is padded away from the boundary of the partition of its cluster by a distance at least t, behaves something like this. It's a ratio between two balls of diameter delta and delta over 8. And this is to the power of t over delta. Okay, I won't prove this lemma. It's not very hard. It's actually quite easy. But using this lemma, we can now prove the theorem using a probabilistic method, simple argument of probabilistic method. First moment argument. We just sample at every scale of power of which is power of 8. We sample a partition from this distribution. And now we check what is the probability that a point is epsilon times the scale padded in all scales. So this is this event. The probability that the point x is epsilon delta I padded in its partition in the I scale. Because of the stochastic independence of the partitions, this is the product, and fortunately, this is a telescopic product in which you have in the numerator you have the singleton, in the denominator you have the whole space, which is the side of the whole space, which is n. This means that the number of points is the probability is at least n to the power of 1 minus epsilon, which means that the set of the points that are epsilon padded in all scales has expected cardinality of n to the power of 1 constant times epsilon, which is exactly what we promised. What I promised at the beginning of the theorem. Now let's switch to the variant with the Hausdorff dimension. So first of all, definition of the Hausdorff dimension. So we need the definition of alpha Hausdorff content in the following thing, the following formula. It means that so if you try to cover a space X by balls of radius Ri, you take such a cover, take the radiuses to power alpha and sum it up. Now, if alpha is large enough, then the infimum would be okay, and the space is of constant dimensions. Then this infimum would be 0. Let's take. Let's look at an example. Think of the simplest example that you can think of. This the interval 0 to 1. I want to show that okay, this definition is very suitable to prove upper bounds on the Hausdorff dimension. So I want to show that okay, the Hausdorff dimension is defined to be the smallest alpha for which the Hausdorff content is 0. Okay, it's the point where it becomes non-zero. This is the alpha, the Hausdorff dimension. So let's prove that the Hausdorff dimension of the interval is 1. To prove it, let's take alpha larger than 1 and show that the Hausdorff content is 0. And this is actually very trivial. Just partition the interval into m subinterval of length 1 over m. If you take them to the power of alpha, you get m to the power of minus alpha, you have m such intervals. So what you get for this specific cover, you get this expression to be m to the power of 1 minus alpha. If alpha is larger than 0, larger than 1, this quantity tends to 0.
Upstairs you work with the radius and here with the diameter, but it's not such a big
It's not a big deal. Okay.
deal.
Okay. Okay, another example, trivial example, any countable set has a Hausdorff dimension 0, just because you can cover all points with exponential decaying set of intervals. When you start with the first one will be delta, and then take exponential, and you get this sum to be okay. Exponential to the power of some alpha larger than 0 is still exponential, and okay, it's clear. Okay, so this gives us a definition and a way to prove upper bounds using these definitions. And but now that we have definition, we can actually state a theorem. So in any compact space and any epsilon, we can extract a subset S, which is 1 over epsilon ultrametric and has Hausdorff dimension at least 1 minus epsilon times the original Hausdorff dimension of the metric space. And this is actually tight. Tight even in embedding into Hilbert space. Okay. Okay, but if you look at the theorem, you see that what we need here to prove is a lower bound of the Hausdorff dimension of S. So definition gives us a way to prove upper bounds. We want to prove lower bounds. So it is a simple way to prove
So is this a different S? Does it have anything to do with the previous substance that you constructed?
Previous one win on the finite.
Yeah.
So here, this is what this. I mean, it's different in what sense? It will be different proof. As you
Can you go back one step?
No,
You went
you went
further.
forward. Back into the future.
One more. Okay, I see. Never mind.
Okay. What happened there? Here is a way to prove lower bound on the Hausdorff dimension. So suppose mu is an outer measure, and it's by outer measure it just means that it has I mean that it's monotone, and it has the subadditivity property. And I need two other properties. First, it has positive measure on X, and it has this property that the measure of ball of radius R is at most R to the power alpha. Okay? So someone gave us alpha and such a measure. Then I claim that the Hausdorff dimension of X is at least alpha. Here is the one-line proof. What I want to show is that any cover of X, this expression is bounded away from 0, regardless of the cover. So you see, it's a one-line proof, pretty standard. So by definition, R to the power of alpha is at most the measure of the ball, and by subadditivity, the sum of the measure of the balls is at least the measure of the union, and by monotonicity, the measure of the union is at least the measure of X, because it's a cover, which is by assumption positive. And you see it's bounded below by a positive number independent of the cover. So this proved it. And it is just again, a trivial example how to prove using this lemma that the interval 0 to 1 has a Hausdorff dimension at least 1. Here's the way to do it. You just define a measure on the interval. The measure would be the Lebesgue measure, and you see that it has this property. This is the measure of ball of radius r is at most r to the power of 1 divided by 2. Okay, but let's ignore constants because we can just scale the measure by this constant. And this proves the Hausdorff dimension of the non-surprising fact that the Hausdorff dimension of the interval is at least 1. Okay. So this is good. We have a technique to prove lower bounds, but how do we get this measure? So we have, remember, we start with a lower bound of arbitrary metric space X. We have its dimension. We have a lower bound of its Hausdorff dimension. We want somehow to construct a measure and use it to prove a lower bound on the subset S. So we need the opposite of this claim. Fortunately, we have it. This is a very well-known lemma called Forstmann lemma from the 20s that says that for a compact metric space, X, if you take beta to be smaller than its Hausdorff dimension, then there exists an outer measure on X with the following with these two properties that we just wanted. I mean, it's the measure of the balls are at most r to the beta, and the measure of the whole metric space is positive. So now we can start with the metric space X, find using Forstmann lemma, extract a measure on X, construct a measure on X. Yeah.
But this is just duality?
It's duality. It's not just its duality, but yeah, I mean, it's duality. You can prove it using, or at least Yuval Peretz know how to prove it using Max Flow Minkat. You know. Oh, Banach. It's a duality argument. Yeah. It's not complicated. I mean, for compact space, it's not complicated. This lemma has more general forms, which are a little bit harder. So how do so this is our main theorem. That are able to connect between this measure on X to a lower bound on S. It's the following thing. Say that for any epsilon, there is some constant gamma, which depends only on epsilon, with the following property. For any compact metric space with outer measure on it, there exists a compact metric measure space, whatever. There exists a subspace of X, a subset of X, which is, as you may expect, 1 over epsilon approximate ultrametric. And the second bullet says that this subset is large. Large in what sense? In the following sense. For every cover of this subset with balls of radius ri's, if you take these balls, you inflate them by a factor, their radius by a factor of gamma, take the measure of the inflated balls, and take this measure to the power of 1 minus epsilon, and sum it up, you get something which is at least the original, the measure of the whole space to the power of 1 minus epsilon. So it's a little bit complicated, but it unifies both the finite Dvoretzky theorem and the Hausdorff version into one theorem. Let's see it. So first of all, this is actually a generalization of the finite metrics of the finite space. The Dvoretzky theorem for finite metric spaces. And the way to see it, so if X is finite, then you can take the counting measure on it. And this theorem says that you can find inside it a subset S which is 1 over epsilon approximate ultrametric, and it has this property which works for any cover. Now all you need to do is to use the trivial cover of S by singletons, by balls of radius 0 around the points of S. If you do that, the left-hand side becomes just the cardinality of the subset S. The right-hand side is the cardinality of x to the power of 1 minus epsilon. So this is a strict generalization of the finite space, but it also proves in 3 lines, it proves the Dvoretzky theorem for Hausdorff spaces. Here is how. Let's fix a metric space X, compact metric space, epsilon, and beta to be smaller than the Hausdorff dimension. By the Forstmann lemma, we have a measure mu, which has positive measure on X, and it has this measure of ball of radius R is at most R to the beta. We apply this covering theorem from the previous slide, and we get a subset S, which is 1 over epsilon approximate ultrametric. And now we want to show that it has large Hausdorff dimensions. How do we do it? We show that for any cover of S, any cover of S has any cover of S by balls of radius Ri have this expressions bounded away from 0. How do we prove it? So this is the expression we want to prove it's bounded away from 0. We multiply and divide by gamma. So now you have this expression inside the sum. So gamma Ri to the power of beta, you may recognize it is at most the measure of balls of radius gamma Ri. So, and now you apply here you can apply the theorem. We know that this is at most the measure of x to the power of minus epsilon. And this is a positive number which is independent of the cover that we took. So this proves that the Hausdorff content of S, the 1 minus epsilon times beta Hausdorff content of S is positive, which means that the Hausdorff dimension of S is at least 1 minus epsilon beta, but this was true for any beta smaller than the Hausdorff dimension of X. So we just proved the theorem for the Hausdorff case. So let me just give you another somewhat stupid example that shows that the statement of the covering theorem is strictly stronger than the finite theorem. So here's an example. It's a little bit simplistic. So assume this is a condition. We have 1 minus epsilon to be 1/3. Here is a solution for the finite Dvoretzky theorem. These 3 points are close to be equiliteral, which is ultrametric, and 3 is at most is larger than 18 to the power of 1/3. I checked it. However, this is not a good solution for the covering theorem. Why? Because there is a bad cover here, which, for example, if you take this cover, okay, this is a cover of the subset. And now you inflate it by a factor of gamma. The content of this, the measure of this ball is only 5. And last time I checked, 5 to the power of 1/3 is smaller than 18 to the power of 1/3. And however, there is a good solution here. For example, if you take this triangle, this is a good solution because any cover of it would have this property that I want. For example, if you take, again, a cover by one ball, this cover, if you inflate it by a factor of gamma, you get the whole space, and obviously we have this inequality. Okay. So now I will try in the rest of the time that I have to outline, or to try to, I won't prove the, okay, I will send the, I won't prove the theorem, but I'll at least try to explain how one may approach the proof for this thing. So let's approach it using this assumption star. Assumption star is the following assumption.
So we're proving the general. Well, this is a description for what?
For a proof for this theorem. For this theorem. Okay. And let's say it's approach for the proof. It's not really a proof. So let's assume assumption star. The following assumption: suppose you have gamma and 1 minus epsilon with the following property, that any compact metric measure space we can find of diameter delta, we can find subsets y1 to yl, which are separated by a factor of, by a distance at least delta over gamma, and have this property that the sum of the measures of yi to the power of 1 minus epsilon is at least the measure of x to the power of minus epsilon. Suppose, so this is a picture, we have this x, we find subset 1, y1, y2, and y3, which are separated by a distance delta over gamma, and the sum of their measures is at least the measure of x to the power of 1 minus epsilon, at least the measure of x to the power of 1 minus epsilon. Suppose we have this assumption. How do we construct the subset? It would be actually very simple. We start with the whole metric space. Suppose its diameter is delta. We apply the assumption. On the first level, we find these subsets. And now we apply recursively this assumption to each of the subsets. And we continue this way ad infinitum. And the resulting, you can actually define a tree on this structure, and the branches of this tree would be the subset of points will correspond to the subset S that we want to find. This subset is obviously gamma approximate ultrametric because of the conditions that at every level they are separated by the diameter over gamma. And I want to prove that it has this covering property. Okay? So to prove the covering property, let's prove a cut set property. What is a cut set? So a cut set in a tree, by cut set in a tree, I mean a set of vertices which intersect any branch in the tree, infinite branch in the tree. And I want to prove that in any cut set, the sum of the measure of the points, of the vertices is just subset in the space. So the measure of the vertices in the cut set to the power of 1 minus epsilon is at least the measure of x to the power of minus epsilon. And okay, this is for any cut set, but to prove it, it's sufficient to look on minimal cut sets which intersect every branch at exactly one vertex. And the minimal cut sets in tree with finite valency are a finite subset. This is standard compactness argument. So we have finite, the cut set is a finite subset of vertices. What we do now, we apply the assumption star on the lowest level. So it takes the deepest vertex in the cut set. All its sibling must be in the cut set. Okay, and so we can apply the inequality from assumption 1, which says that the sum of the measure of z1, z2, z3, z4 to the power of minus epsilon is least the measure of y3 to the power of minus epsilon, and we can diffuse this property up until we reach the root. In that case, we finish the proof of the cut set property. Okay, using the cut set property, we can actually finish the proof of the lemma. So now we have, let's fix the notation. We have this metric space X, compact metric space. We found the subset, the branches of the tree, which gamma embedded in ultrametrics. I want to call the ultrametric, I call it rho. So rho is at least dominates delta, but is at most dominated by gamma times d. Okay. So now let's look on rho. So what is a rho ball? In this rho ball is just what is a ball in the row metric is just a subtree, infinite subtree, repeated at some point in this tree. So row ball cover of S correspond to a cut set in this tree. Okay. Now let's look on D balls. Every D balls is contained in row balls by when you inflate the radius by a factor of gamma. This is just because of this inequality. Okay, so D balls. So if we begin with arbitrary cover of S by D balls, when you look on row balls, they corresponds to cut set in the tree. So this is basically finish the proof, because if you look on now, if you start with D balls of radius gamma Ri, they contain the row ball. So they actually contain the vertex in the tree. So they contains cut sets. So you can put everything together. So the measure of the row of the D balls of radius gamma Ri is at least the measure of Ai. And now here, and this is the cut set property that I just proved. So let's finish the proof, assuming a substance star, but we're not finished yet because two things. It's not one, it's two things. First of all, the gamma that we get in this argument, we get something which is exponential in epsilon, actually in epsilon squared, in 1 over epsilon squared. And I want the distortion to be 1 over epsilon. Gamma becomes a distortion here, so it's not good. And the second thing, which is more severe, is that actually we don't know how to prove assumption star. This is why I call it assumption star. But I didn't waste your time because it seems it's at least this is the way we thought about it. We can prove something a bit weaker. Let's call it star prime. Star prime, lemma star prime will have the same structure. We'll find subset which have this inequality, that the sum of their measure to the power of minus epsilon is the sum of the whole space to the power of minus epsilon, but the separation property would be weaker. What we have is actually this thing. So we found subsets which are not separated, but they are of very small diameter compared to the diameter of the original space. And you can find some scale in between in which you see actual separation. Okay, so you see these two clusters are not separated, but you have some clustering of the intermediate clustering in which you see separation. And this is actually good enough, because if you think how I applied assumption star, I applied it now it was a top-down application in which I replaced I applied it to each of these small clusters in smaller scale. So if I applied this intermediate separation in a lower level, will give me a separation, smaller separation. It won't be gamma, it will be gamma squared. But what is a square with this exponential in epsilons? Anyway, it's bad enough. So, but this is good enough. So this is what we have. If you apply it top down, the ith one plus one level creates a separation for the ith level. So it's good enough. The high-level approach is a little bit disappointing in the sense that the reason that I described assumption star was because it gave a conceptually very simple approach, top-down approach. But this was a lie. Actually, we don't know how to prove lemma. The proof of lemma star prime is actually works by top-down and then a bottom-up approach, a construction, and then top-down specification. So we construct a special partition in a bottom-up way, and then we specify top-down. I won't get into details, but I just say that bottom-up is a little bit problematic because you need a bottom. So bottom, bottom here means this, minimal scales, which means the space has to be discrete, which means compact discrete space is finite. So okay, so it turns out this is not a really problem because everything follows. So the whole proof works on finite spaces. This works on finite spaces, and there is relatively standard compactness argument here. They just use the fact that if I start with compact space, there is a distance on subsets called Hausdorff distance, which is compact. So we can use accumulation. So we take nets in the original space. We apply the finite version of this covering theorem. We find subsets, and this subset has accumulation point in the Hausdorff distance, and this accumulation point is the subset that we are looking for. How long do I have? 10 minutes. Okay. A few words about overall. So this gives us this is actually can be done, but it gives the distortion is a little bit too high. It's exponential in 1/epsilon, and we want to get the tight distortion 1/epsilon, tight up to the constant hidden in the O notation. So what we do, we look again on this lemma lemma prime star that I looked, and we change length, and instead of looking on this level of the small balls, they are supposed to be red balls. Okay, it looks like yellow here, right? Okay. We look on the intermediate level, the white, the blue balls. In the intermediate level, we have separation. What it means by having separation, it means that between two blue clusters, the minimal distance and the maximal distance are roughly the same, which means that we can think of each of the, up to constant distortion, we can think of each of these balls as a point in some finite metric space. And the construction that I just gave you simply map this finite metric space into this is what the Ultrametric construction does. It maps this finite metric space into equiliteral space, which has the high distortion, 1 exponential and 1/epsilon squared. So the question whether we can actually, what we try to do here is to find a refined Ultrametric on this space, finite space of points, and then plug in this refined Ultrametric inside the higher, larger Ultrametric space. Now, this in general cannot be done because there is cases in which the equiliteral embedding into the equiliteral space is the best that you can do. I just show you one example in the beginning of the talk, the path. But what we can do now is apply here on this space, apply of the space of the blue clusters, apply the finite Dvoretzky theorem, a weighted version of it, which is easy, is almost as easy as the unweighted version, and throw away one such region in such a way that the resulting space is close to Ultrametric. Right? And then plug this in. And if you do it correctly, you lose a little bit. You lose a little bit in the power, but you get a right ultra distortion. Now there is some problem here. If you remember, we have this inequality that compares the measure of the cluster to the measure of the whole space, but this one works for the yellow cluster, not for the blue cluster, not for the weight of the blue cluster. So we don't have the cut set property on the blue cluster, so I can't actually apply things. This is very vague at this level, but we can somehow solve it. If you do things a little bit more carefully, we can recover not the cut set inequality, but something a little bit weaker, which is still good enough. However, in the process, we need to find to apply this finite Dvoretzky theorem not to one weight, but to two different weights. So we need to find a subset which is large, which is approximate ultrametric, and it's large in two different senses. It's large according to two different measures. How do we do it? So this is actually a simple solution. We just apply the finite Dvoretzky theorem twice, get two sets, and take their union. Now the reason this is really deep in the proof, the reason that I highlight it in this talk is because it's bringing an issue which is totally unrelated to the whole talk and can be understood even if you didn't understand anything in this talk until now. You still may be able to understand. This is very simple. This is the following question. What is the distortion? So I have two different approximate ultrametrics, and I want to take their union, and I want them to be still an approximate ultrametric. So this is a question. We have two subsets of metric space X. Each one is approximate ultrametric with distortion D1 and D2 respectively. And we ask how well you can embed the union in ultrametric. So here's a bad example. Take just, again, point on the line, m squared point on the line. Take half of them in this way, half of the points, the red points, which are half m intervals, each of length m. It's easy to see that this subset of points can be embedded in ultrametric with distortion a-1. This is just the embedding. I just described the embedding. The other half is, of course, isometric to this one. So you can also embed it in ultrametric with distortion m1 over m-1. But their union is just the m squared points path, which, as we saw at the beginning of the talk, has distortion of at least m squared of -1. This is an example in which the distortion, if you start with distortion D1 and D2, you got D1 plus 1 times D2 plus 1 minus 1. In this example, D1 is equal to D2. What we showed is this is actually almost tight in general. So for any two sets you can get with distortion D1 and D2, you can, their union is approximate ultrametric up to distortion of D1 plus 2 times D2 plus 2 minus 1. Okay. That's it. And so this is actually the main theorem that I discussed in this talk. The covering property is a little bit more general than the way we applied it. We applied it to Frostman measures that have this property that the measure of bolus of radius r is at most r to the power of beta. It's a little bit more general. It works for any measure, basically, any metric measure. So we are looking for other application if you think about it. And this is a little bit premature, but my hunch is that if there are other applications, the bound on gamma would be important. We are able to prove this bound, and I don't think it's tight. So I don't know whether it can be improved. And that's it.
Not a good question before lunchtime. Okay, thanks again.